This video illustrates techniques for calculating the degree of dissociation, alpha, for monoprotic through polyprotic acids. So let's begin by looking at the fundamental equations that we're going to use. For a monoprotic system, alpha HA, which is the fraction of the species in the acid form, is defined as the concentration of HA over the formal concentration. And as we derived in class, this is equal to H plus over H plus plus the first and only acid dissociation constant. And this comes out of equation 1917 in your text. Okay, the degree of dissociation of the, or the fraction of the base is A minus over the formal concentration, and that turns out to be Ka over H plus plus Ka. And again, that's equation 1918. But you can expand this from a simple monoprotic system to a polyprotic system, diprotic, triprotic, etc. And when we talk about EDTA acid-base chemistry, we want to calculate the degree of dissociation for a hexaprotic system. So these hexaprotic acid systems have a denominator, which isn't just H plus Ka, but H plus to the 6th, H plus to the 5th K1, H plus to the 4th K1, K2, etc., all the way out to K1, K2, K3, K4, K5, and K6. And the numerator for these alphas, and this would be the alpha for the fully dissociated form of EDTA, so this would be the 6th fractional species, is K1, K2, K3, K4, K5, 6. And the first species would be H plus to the 6th over D. The second species would be H plus to the 5th over D. The third one would be H plus to the 4th, K1, K2 over D, etc., all the way out. So armed with our distribution functions, we can calculate the degree of dissociation of a weak acid by summing the fraction of the alpha 1 species, the species that's lost 1 proton, 2 times the alpha 2, plus 3 times the alpha 3, plus 4 times the alpha 4, etc., all the way up through, in this case, 6 times the alpha 6 for a hexaprotic acid. And we'll see that this is very helpful in calculating the pH of acid-base titrations. So let's begin with the implementation of these calculations. Here I've listed the pK1 through pK6. The Ks are calculated from the pK1 through pK6. My pH is the master variable in this approach, so pH is going to start as a known, and I've gone from 0 down to 14. I calculate the H plus from the pH values, and then I calculate the denominator as if I were always working with a hexaprotic acid system. So the denominator comes from equation 11-4, and it's H plus to the 6th plus H plus to the 5th K1 plus H plus to the 4th K1, K2, etc., all the way out to K1, K2, K3, K4, K5, and K6. Notice I've used the dollar signs in front of the cell references so that I can fill down easily. Armed with this denominator, I can now calculate alpha 0. Again, I'm going to do it for a hexaprotic acid system. Alpha 0 simply H plus to the 6th over the denominator. Alpha 1's H plus to the 5th, K1 over the denominator. And skipping to the end, alpha 6 is a K1, K2, K3, K4, K5, K6 over the denominator. And then finally, I have the degree of dissociation, which is the alpha 0, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, scaled by the number of protons that are lost. Okay. Now, the advantage of writing a hexaprotic acid system is it gives us a general equation set, and we can treat this as a simple monoprotic acid by simply setting the first pKa to a reasonable value, 5.5, and the rest to a value of around 25. And this is essentially like saying that protons on acetic acid, except for the proton on the carboxylic acid functional group, are clearly protons there, but they don't come off the molecule. This is another way of saying that the leveling effect means that the pH of the solution will never be greater than 14, and so a acid-base species with a very high pKa won't come off. You can also think of this as just a simple algebraic trick, and it allows us to now draw the distribution function for a simple monoprotic weak acid. There's alpha of 0. It goes to 50% at the pKa. It decreases as you increase the pH, and your alpha 1 increases, again, 50% at the pKa, and increases to 1 when you get about 2 pH units past the pKa. In this case, the salmon-colored line is the degree of dissociation. 0 at low pH, 50% at halfway through the titration, 100% 2 to 3 pH units past the pKa. So this is quite helpful, and now we can now use this to estimate the pH of acid-base titration. So in this case, I have a weak acid, 0.01 molar. I have a volume on weak acid, 100 milliliters. My strong base has an equal concentration, so the equivalence volume should be 100 milliliters. Let's say that we've gone about 40% of the way there. So my degree of dissociation is 0.4. What would the pH be? Well, we could come up here and we could scroll down till we get to 0.4, and that says it's somewhere between 5 and 5.5. Or we can use goal-seek to find that value. So what I've done here is I've created a new fit, and it's just one line of this piece up here. Notice I've got pH. That's going to be my fitting variable. H plus, which is a function of pH, and then I've got the denominator and A0, A1, A2, A3, A4, A6, all the way out to the computed degree of dissociation. So if I want to guess what the pH should be, I can do a little guess and check, and I can say, well, 5.3. 5.3 gives me a value of 0.38. I should go a little higher, 5.4. That's a little too high. So somewhere between 5.3 and 5.4 would be the pH if I added 40 milliliters to a 0.01 molar solution, 100 mils of a 0.01 solution of a weak acid. Now, using goal-seek, I can come in here and I say, I want that cell, which is the computed degree of dissociation, to be exactly 0.4, and I'm going to do it by changing the pH. So now it's going to move the pH up and down until my fit parameter equals 0.4. I hit OK, and we're done. So the pH was somewhere between 5 and 5.5. It's actually 5.32. So 5.32, and you notice these two agree quite well. Well, that's a pretty easy calculation to do directly if you have a monoprotic system, but not so easy when you have a hexaprotic acid system, and not easy at all if you had multiple acid species in solution. So if you had 2 weak acids in solution, you could add the end fits for both acids together and fit that sum to calculate the pH. All right, well, let's move from a monoprotic system to a hexaprotic system. So I pasted the pKa's for EDTA out here just for some housekeeping convenience, and I will paste them in. And when I do that, you'll see that my alpha functions now are quite a bit more complicated because I don't have a monoprotic system, I have a hexaprotic system. There's alpha 1, alpha 0, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, and alpha 6. And you can see that the degree of dissociation now maxes out at 6 and starts at pH 0 at a value of about a half because the first 4 dissociations of EDTA are all really quite acidic. So now these all have real values. The degree of association starts at about a half and it increases up to 6. And now you can come in and say, all right, let's assume we started with EDTA at 0.01 molar. I had 100 mils of it. My strong base was 0.01 molar. Concentration of the base, the volume of the base. We'll go ahead and assume that we're going to put in 4.5 equivalents here. So that's going to be 0.47. We'll make it a little interesting. Okay, so that means we're going to try to get to a degree dissociation of 4.7. And it looks like that pH was just about the right spot. Need to make it a little higher, so we'll go 5.6. Yeah, I can go a little higher than that. Let's go to 6.3. And we're getting close. And of course, the easy way to do this is to go to goal seek. Tools, goal seek. We're going to make that cell equal 4.7. Notice I'm typing in the value here into my 2 value by changing the pH. We hit OK, and we're done. So at a pH of 6.497, I would be the pH of a solution if I took 100 millimolar of 100 mils of EDTA and titrated it with strong base.